All right, brand new unit. We're doing quadratic functions. So hopefully this will look familiar because we've already been doing quadratic functions. Quadratic functions are functions that have a square in them. So when you think about functions, we've done linear functions, which was y equals mx plus b. Now we're doing quadratic functions, and y equals ax squared plus bx plus c. So everything we've been doing in factoring so far has been leading up to doing graphing and finding all the parts of quadratic functions. So let's get started. All right, quadratic parent function. If you'll remember when we did linear parent function, there was one parent function and one parent function only for any line, and that was y equals x, or sometimes we said f of x equals x. So if we have a quadratic parent function, because quadratic has the square, the parent function is y equals x squared, or f of x equals x squared. So it kind of looks the same. Linear has just a single x, quadratic has an x squared. So let's write the equation since I just did. Okay, so if we're going to put let's do the table. If we're going to put our x values in to our equation and square them, our y values are going to be squared. And if it's a negative number, -3 times -3, it's going to be positive. So y is never negative when you're talking about a square. So we have 9, 4, 1, 0, 1, 4, 9. So as you can tell, we're going to have a point at 0, 0, point at 1, 1, and a point at -1, 1. I don't know how to make those show up better. I have a point at 2, 4, and a point at -2, 4. I have a point at 3, 9, and a point at -3, 9. So it makes this great parabola shape. You're supposed to try to make a really smooth line. It doesn't come to a point at 0, 0. It kind of is supposed to be smooth, which mine's not very much, but that gives you the general idea. It's going to look like a parabola. It's going to start always at the origin, or that's going to be the vertex, which is a new word we're learning, is the highest or the lowest point. And it should be smooth, and it's symmetrical. It's got the same on both sides. So the domain is always going to be all real numbers. Oh, that's weird. Okay. That's really weird. Let's see. It doesn't like it when I try and write in these boxes, that's for sure. Okay, so the domain is going to be all real numbers. So I'm going to do that. That's my all real number sign. The range is always going to be y greater than or less than. This case, since it's going up, it's going to be greater than or equal to 0, because there's no y values that are negative. They're all positive above 0 or equal to 0. The vertex is that very top or very bottom point. In this case, it is 0, 0. Our vertex is a minimum because it's the lowest point. Our concavity, think about like spoon or something that's concave. This one is up, so we're going to say concave up. Our choices are up or down. And the line of symmetry is the vertical line that goes through the vertex. In this case, it's going to be x equals 0. Remember, it's a vertical line, so it'll be vux. And in this case, it's the y-axis. And so x is equal to 0. So that's the parent function. And that's always the point kind of we start with. And then as we add things to the quadratic equation, it shifts it up or down. It can flip it up or down, and it can make it more wide or more narrow. And we'll talk about that later. All righty. So let's go ahead and label our graph. Let's see. This is the axis of symmetry. And I know that because it goes through my vertex, which means this is my vertex. The axis of symmetry goes through the vertex. And these places right here where it crosses the x-axis are our solutions. We also call them roots. We also call them zeros because x is 0. I don't know if there's any in zeros. Or you could call them your x-intercept. Or you could call them, I guess that's it. Okay, and I kind of feel like there's another name, but I can't think of what it is. So anyway, once we start graphing these on the calculator and solving them, when we're finding the solution, it's going to be the place where it crosses the x-axis, and there's usually going to be 2 of them, but not always. It's kind of those, yeah, anyway. Okay. So let's talk about lines of symmetry. Here is our equation for the standard form of a quadratic equation. Okay, and we have 3 different graphs that we're going to look at the lines of symmetry. So these all have a vertex we can find. The vertex for this one is -2, 2. So our line of symmetry is a vertical line, x equals -2, and it's whatever the x value is. Okay, so here's our function. Should we go across or go down? Let's go across. Okay, vertex for the next one. 2, 4, which means the line of symmetry is x equals 2. And our next one is going to be 1, -4, which means our line of symmetry is 1. Okay, here's the functions right here. So we have a, b, and c. We're always going to want it to be y equals for this. A is in front of the x squared, b, and c. So a is -2 and b is -8. Another way to find the line of symmetry is, see if it moves it in a weird spot. Is not really b over a, so I'm going to cross that out, and it's really -b over 2a. So when you do -b over 2a, that's going to give you the value of x in your vertex, which is also your line of symmetry. So for this first one, when a is -2 and b is -8, there's always a negative sign in front. So whatever I have, I'm going to do the opposite. So I have -8 and -2 times 2. So I have 3 negative signs. A negative divided by a negative is positive. But then I have another negative sign, so it's going to end up being negative. 8 over 4, which is 2, which is the same as our line of symmetry we had up at the top. How about that? Okay, so the second one is missing its C value. So you could think about it as having a plus 0, but we don't need that because we're just doing A and B. So A is -1, B is 4, and so the axis, the line of symmetry is going to be -4 divided by -1 times 2. Two negative signs make it positive. 4 over 2 equals 2. And that's the same as what we had up here. All right, last one for this part. A is 1, B is -2. So again, we have a -2 over 2 times 1. So the negatives cancel out, and I have 2 over 2, which is 1. So it worked out. How about that? All right, so let's look at the next problems. Now would be a good time to pause the video if you want to try it yourself. The line of symmetry is x equals -b over 2a. So, number 1, a is -2, b is 1/3. So the line of symmetry is going to be -1/3 divided by -2 times 2. So let's think about what happens. First of all, my negative signs cancel out. So I have 1/3 divided by 2 times 2 is 4. I can think about, hopefully you remember, flip, keep, change, or whatever. I can change that to 1/3 times 1/4, which equals 1/12. So x equals 1/12 would be my axis of symmetry. So now I'm looking going, did I make a mistake? Because I don't think that's what I got last time I worked this out. Okay. It's a -3 1/3. And it's 2 times -2. So it's -4 divided by 1/3, -1/3. And it looks good to me. Okay. So x equals is our axis of symmetry. Okay. So the next one, notice that we're missing something. We're missing our b. So a equals 1, b equals 0, which solves that problem right now because I have 0 over 2, which is 0. So x equals 0 is my, so it goes through the y-axis is the axis of symmetry. Last one, okay, a equals 5, b equals -20. So we have -20 over 5 times 2, which is 10. My negatives cancel out. 20 divided by 10 is 2. So we have x equals 2. Okay. So if I need my equations in standard form, we're going to always put everything on one side, and it's really equal to y. So we could think about this as, I'm going to go ahead and do -3x squared, -3x squared. So I end up with a 0 over here, which really is y, -3x squared minus 5x plus 4. Remember me saying stuff about we don't really like having a negative in front. We do sometimes, but I'm going to go ahead and multiply everything through by a -1. I'm going to change all the signs, and I'm going to have 3x squared plus 5x minus 4. So there's our equation in standard form. A equals 3, B equals 5, C equals -4. Okay, so that is the line of symmetry, which is the place that the vertical line that goes through the parabola that's exactly through the vertex and it's symmetrical on both sides. Okay, so now let's find the vertex and see if we can notice something tricky for finding the vertex. Alrighty, I'm gonna introduce you to the other way we can write these equations. So our vertex, I have my equation right here, but what I'm gonna do is I'm gonna look at my vertex. So it's at the point 2, -2. My line of symmetry is x equals 2. It's a minimum because it's the lowest point. It's concave up because it looks like a smile. The domain is all real numbers. And the range is y greater than or equal to -2. Because -2 is the lowest value y can be, and it can be anything up to infinity after that. Okay, so for the next one, the vertex is -2, 6. The line of symmetry is x equals -2. This one is a maximum because it's the highest point, so it's concave down. The domain is still all real numbers, but now the range is going to be less than or equal to 6 because it never goes above 6. Okay, here's where it gets kind of weird-ish with the equations. Okay, so when you have an equation, here's a new different looking equation. This equation right here is called the vertex form, is usually what it's called. And the reason it's called that, and I'm going to go ahead and give you some letters which you may or may not ever use again. But I have more room at the bottom than you do, so you may have to get creative in how to take these notes. The vertex form is y equals x minus h squared plus k. The vertex is h comma k. Notice that I don't take the negative sign with me, it's part of the equation. So just like we had equations with our lines, point slope form gave us different information than slope intercept form, than standard form. This vertex form is nice for finding the vertex because it's just right there. But it makes it a little different when you're looking for more different information. So to solve the vertex form, we're going to do just what you would expect. We're going to expand, which is x squared minus 6x plus 9 plus 2, and then we put that plus 2 on the end. Here's my expanded version. I'm going to simplify and combine these two terms, so I'm going to end up with y equals x squared minus 6x plus 11. Because a is positive, and I meant to mention that up at the top somewhere. I meant to talk about that up here. I'm not doing a very good job. Okay, so we have a, which is in front of the x squared. If it's going this way, wait a minute. No, I have to think about that. If a is negative, it opens down. Okay, notice a is negative. If a is positive, and I just wrote it off the page, then it's going to open upwards. So this is the normal way you see it, is opening upwards. From our parent function, we know that. So when I'm looking at all that to say, when I'm looking at this equation that I wrote, x squared minus 6x plus 11, it's going to open up, and I'm going to have a minimum. The vertex is 3 and 2. I don't take the minus sign with me, it's just part of the equation. Okay, now I don't know my line of symmetry until I do this. So now that I have this, because when I have the one above, I don't know what A and B are. I have a equals 1 and b equals -6. So -6 over 2 times 1, positive 6 over 2, which is 3. So the line of symmetry is x equals 3. Oh, duh, because it's right here. Okay, I'm an idiot. It's concave up because it's a minimum. The domain is all real numbers, and the range is y greater than or equal to 2, because that's our vertex number. I didn't really need to do that, did I? All right, extra information right there. Bonus, because we didn't really need to do that. I made that up. Okay, second one is already in standard form, not in vertex form. So let's see what we can figure out from this. For this one, we're going to have to do a equals 1, b equals 6. So we have -6 over 2 times 1, which is -3. So the vertex is x equals -3. Oops. X equals -3. Yeah. I'll figure this out. I haven't made half as many mistakes as I normally do that you guys never see because I always start over. Okay. I do not know. Well, I know the domain is all real numbers. And since A is positive, I know that it has a minimum and it's concave up. I don't know what else I know. I don't know what else I know unless I graph it. So now I'm going to show you how to change it back to vertex form. Okay. I should have a whole day. Maybe we'll do this in class tomorrow. It's called completing the square. Remember those perfect square trinomials that some of you were like, oh, I don't like perfect square trinomials. Well, now they're going to come back to haunt us. Okay, I'm going to take my x squared plus 6x, and I'm just going to forget about my plus 4 for a minute. I'm going to just put it over there. Okay, I would like to complete the square so that I can end up with something like I had in my vertex form where I have the same binomial squared. So if I'm looking at this, I'm thinking, especially if x is 1, if this is a 1 right here, this number is going to be k times 2, and this is going to be k squared. So I'm doing a lot of mental math because remember, if I have k squared and whatever it is, k doubled, remember I end up with that. So I'm going to go ahead and put in a 3. 3 squared, oh no, I'm not. 3 squared is 9. 2 times k is 6. So I end up with 1x squared plus 6x plus 9. I didn't need to rewrite that. Okay, so I end up with 1. Okay, deep breath. I'm worried about running out of room. Okay. So what I'm writing is k. I have x plus k, and k in this case is 3 squared plus 4. And that's not right either. Okay, we're going to stop right here, put a big old fat question mark, and we're going to talk about this in class before we start our practice.